Okay, you guys, natural selection with goldfish. The first thing you're going to want to do is find something that you can use to actually do this activity on your own. It's I don't know, much more beneficial if you can at least kind of make it hands-on in some way. If you don't have goldfish, that's fine. Just get like two different types of snack foods or crackers, M&Ms, whatever it is that you have, just two distinguishable types of snacks that you can remember which is which. We want one of them to represent the dominant trait. And so in this case, our brown fish are going to be dominant, and our orange fish, the orange color is going to be the recessive trait. And if you remember back to our genetic stuff, if you are an orange fish, that means you have to have two of the recessive allele. And so that's kind of our go-to fish for doing all of the calculations in this lab. So whatever your recessive trait is, in order to display that phenotype, the recessive phenotype, you have to have two of those recessive alleles. So that's kind of one of the key things to remember for today. So in this experiment, what we're trying to basically simulate is that we have fish in a pond, and we have some orange fish and some brown fish. And we're saying, okay, what if this pond is really muddy? Because that's pretty common in ponds, and you are a predatory fish, and you're going to look for these little orange and brown fish trying to eat them. So this is like your main diet, are these little orange and brown fish. Well, if the pond is very muddy, what are you going to be able to see more easily as that predator? Probably the orange fish, right? They'll probably pop out a little bit easier against a muddy background of that little pond water. So what we're going to simulate today is that orange fish are going to be predated upon or eaten much more frequently in this population than brown fish are. And we want to know over time, how is that going to affect the population numbers of the orange and brown fish? And this isn't a trick. The results are going to be pretty obvious. You're going to expect that the orange fish numbers will decrease in the population, and that is exactly what you should end up seeing. So we're just going to kind of simulate how that would play out in a real population. Of course, we're using crackers or whatever it is that you have at home, but things like this can happen in the real world. Now, the one thing that we're doing that doesn't always happen in the real world, and actually almost never happens in the real world, is this thing called Hardy-Weinberg equilibrium. If a population is in Hardy-Weinberg equilibrium, that means a series of things. It means that essentially evolution is not occurring. So you're saying that the orange fish are going to be predated upon more, they're going to be eaten more frequently, but this population of fish is not going to respond to that predatory action. So they're just going to remain the same over and over again. That's kind of your null hypothesis. So if you remember back to when we first started talking about the scientific method way in the beginning of this quarter, no evolution is kind of the null hypothesis in this case, and that's what Hardy-Weinberg equilibrium would have us believe. And so based on the idea that evolution is not happening, one good thing from that is that we can really easily predict the allelic frequencies in populations, because evolution at its base level, like at its most basic definition, is a change in allelic frequency over time. So if Hardy-Weinberg equilibrium is at play, that means evolution is not happening. That means allelic frequencies are not changing. And so we can always predict the allelic frequencies or calculate the allelic frequencies, because they're not going to change between or within one generation. So we have some steps written out here for you. If you get a little bit confused by it, just kind of always come back to steps 4 and 5. These are the two that you're going to repeat over and over again for 5 populations total, or 5 generations, I should say, total. And all the calculations that you need to make are based on these variables. So P, Q, P squared, 2PQ, and Q squared. P is just the number of dominant alleles, or the frequency of your dominant alleles. So I would usually use like a big A and a little a for these things. So P would be the big A, Q would be the little a. PQ, can you guess what that would be? It would be A, big A times big A, which is your homozygous dominant individual. 2PQ, if you remember your little Punnett square, if we did a Punnett square, and I can show this to you in a second, if we did a Punnett square between a big A little a parent and a big A little a parent, 50% of their offspring would be big A, little a. And so that's what this 2PQ, that's why you do it times 2, is because the frequency of those offspring, 2 out of every 4 of them would be big A, little a. And then finally, you have little a, which is your Q squared. And this is always going to be the easiest one for you to calculate today. So always kind of come back to this Q squared value. We know what the Q squared is. It's a homozygous recessive individual, and those are going to be our orange goldfish crackers. The tough thing is that our brown goldfish crackers, or our brown little fish, they can be big A, little a. They can also be big A, because that recessive gene, recessive allele gets covered up by the dominant one when they're expressed together. So we cannot ever know what the actual genotype of a brown goldfish is. We can only know the orange ones. And so we'll always calculate these guys first, the Q squared, and then we'll get all of our other values from these two equations up here. So P plus Q equals 1. That just means that the number of the big A alleles and the number of little a alleles, when you add them all up, it has to equal 100% of your population. And it's just simple math. I mean, if it didn't equal 100% or 1, then that would mean that you have another allele in the population that you just haven't even taken into account yet. But for today, you know that these are going to be the case. P plus Q equals 1, P squared plus 2PQ plus Q squared equals 1. And so we can use these to calculate all of our allelic frequencies from here on out. So I would just suggest what I had everybody do in class was just basically start with 8. I actually think that we started with 8 orange goldfish. Let me change this really quick. Start with 8 orange goldfish, or whatever your recessive is. And I already wrote out your first line of math here for you. I wanted you to have something to come back and reference if you get confused by this math later. So just go ahead and whatever you're using, if it's 2 types of crackers, if it's 2 types of snacks, M&Ms, and something else, then just make 8 of them be your recessive, 7 of them be your dominant color. And again, the dominant can be big A, or big A, little a. So when we go to calculate our allelic frequencies, the only thing that we can do first is calculating our Q squared. And so our Q squared is going to be 8 out of 15, because we're going to start with 15 fish total every single time. So 8 out of 15, that means 8 out of our 15 fish are orange, or little a. So again, don't overcomplicate it. It's pretty simple. That's just the frequency of orange fish in your population, which is going to be 0.533. And just using those equations from above, I calculated everything else here. So 1 minus Q is going to give me P, and how I got Q was just simply taking the square root of Q squared. So we're just doing some very basic algebra here, but if you get caught up in this, just let me know and I'm happy to help you through it. Okay, after you do that, I have a place for you to put your starting allelic frequencies, which are going to be what I calculated in the first row here. So 0.27 and 0.73, those will be your starting allelic frequencies. And I want you to put the ending ones right below them, just so you can make a really quick and easy comparison when you get done with this little experiment and answer your questions more easily down here. So at the end of all this, you're going to say what happened to each color of fish and why. Did your original predictions agree with the outcome? If not, how did they differ? And I'm going to guess that you will at least partly support your prediction. And I don't really care if you support your prediction. All I want to know is, how did they differ, or why do you think you were wrong? So just explain to me, why you didn't get the same results as you thought you did, or why you did get the same results. So either way, just explain it and you'll get the full points regardless of what you ended up predicting. Okay, which trait is favorable? Well, I already talked about this. So just go back to the beginning paragraph and it kind of sums it up nicely. So we're talking about a muddy pond and a predator that is hunting orange and brown fish. Obviously, brown fish can hide easier. The orange trait is then not favorable. Phenotype just means the physical trait or the physical characteristic. The only tough question, in my opinion, is this one. So did the phenotype disappear from this population? Why or why not? It kind of depends on your experiment. And so it's kind of a luck of the draw situation. And I'll explain that in a second. So I'll come back to that question. Explain why the recessive allele does not disappear. So it's possible that you will answer yes to this. And obviously that would affect this question right here. But I will explain this a little bit. This is always going to be a possibility. And I'll explain to you essentially why this is a possibility that the little a allele does not disappear, or how we can basically always say that it's not going to disappear. And then did evolution occur? Remember that evolution is simply a change in allelic frequencies. So if your allele frequencies change from starting to ending, you have to say that yes, evolution did occur, because that is the definition of evolution. Okay, and then just go ahead and paste. I don't care what you end up doing for your experiment. Use whatever you can, whatever is easiest in your house, and then just show me that you at least attempted to do it on your own at home. And then obviously, if you have any other questions, just let me know. I'm going to go ahead and share a little picture that I have set up on here. And if you want to do something similar, you are welcome to. So I just drew out some goldfish because I don't have goldfish crackers, but I wanted to show you kind of with the colors how this would have worked in lab. So if we have orange and brown goldfish, and I say that they are in a muddy background, so a muddy little pond, you can already kind of immediately see that the orange goldfish are probably going to be more easily picked apart. And if you think about a pond itself, the orange ones are probably going to like reflect sunlight a little bit better as well. And so they'll look a little shinier in the water, be much easier for a predator to see in the mud. So what I would do is right off the bat, I have 15 fish. So 1, 2, 3, 4, 5, 6, 7, 8 orange goldfish, and 1, 2, 3, 4, 5, 6, 7 brown goldfish. For each generation, what you're going to do, calculate your allelic frequencies from this set of fish right here. So to calculate my frequencies, I'm just going to simply take 8 divided by 15, and that's my little a, do the rest of the calculations like I have for you already on the Word doc. And then you're just going to take away 3 orange fish from your population. You're the predator, you come in, you eat 3 orange fish. What you have left then is 8 minus 3, so 5 orange goldfish, and you still have 7 brown goldfish. And so you could at each step kind of, calculate, okay, what's the frequency now of the orange goldfish after this predation event? But instead of doing, kind of each step of the calculations, all I want you to do at this point is randomly, and this is why it's good to do it with like real things like crackers or M&Ms, randomly pull out from your source population 3 new fish. So if I have a bag of 20 orange goldfish and 20 brown goldfish, I'm just going to pull 3 more of them out. And, maybe for my next generation, maybe I just so happen to pull out 1 orange goldfish, but then I end up pulling out 2 more brown goldfish. But each time you do this, and why you should start to see a decrease in the orange population is because every time you are going to eat 3 orange goldfish. You're going to randomly draw 3 new ones out of the bag. Maybe you'll randomly draw an orange one every time. Maybe one time you pull out 3 orange goldfish, and so that would kind of be like a null, kind of canceling out your predation event for the orange goldfish. But over time, you should start to see a decrease in the number of orange goldfish in your population. So if I go through and do that for 5 generations, I should be able to calculate allelic frequencies for all of them, always basing it off of the number of orange goldfish in my population. So do your calculations here after you draw your 3 new fish out of the bag, not immediately following the predation event. You always want to do it based on 15 total fish on in your population. So essentially, you're going to allow them to reproduce, say it's like the next summer after they've allowed their population to kind of bounce back from the predation event, or however long you think it takes for goldfish to reproduce. So if you end up having more questions, just let me know. I think the main thing that maybe I didn't mention at the beginning, start with a source population of equal numbers of both fish. That way you have an equal chance of pulling out brown or orange every single time. That's the main thing that I think you need to know how to do. I think I covered all the bases of kind of where people struggled in class, but if you end up having questions, just let me know and I'm happy to help you with whatever else you need.